Hey guys, a few videos ago I derived the equations of motion for an object going around in a circular path. In other words, a path which has a constant radius from your origin. Right? But in this video I'm going to go one step further and I'm going to derive the equations of motion for an object going around in any arbitrary continuous path. So let's say we've got a path like this. Notice that it's not a circle, it doesn't have a constant radius, right? I'm going to see if I can derive an equation to describe this motion. So a small practical example to give you a little bit of a feel for what this could be. This is the y-axis, this is our x-axis, and this path could be something as simple as, say, a footballer running across a field or something like that. And let's say we wanted to find out its position vector. We wanted to find out the velocity of that football player at any arbitrary point in time t, like say right there. And let's say we also wanted to find its acceleration of this footballer running along this football field, for example. Well, first things first, we need to notice that this is our I-unit vector because it's in the direction of x and it's got a magnitude of 1. This is our j-unit vector and it's got a magnitude of 1 as well. And this right here, this little arrow, is just going to be our position vector, r. And most importantly, I'm going to denote capital R as our magnitude of our position vector. Right, it's going to be our magnitude. And notice that r is a function of time because our radius is not constant, unlike with the case of circular motion. And I'm also going to call this angle between the horizontal and our line theta. Right? Okay, well, let's get started. First of all, we know that we can split our position vector into both horizontal and vertical components. Right? And we know we can do that. Let me just magnify it. This is our position vector of magnitude r, right? We know it's got a positive position in the y direction and a positive position in the x direction, and this is going to be theta, meaning this is going to be r sine theta, and this is going to be r cosine theta, meaning that we can write our position vector now as r cosine theta times the I-unit vector and r sine theta times by the j-unit vector, right? And this is just fancy notation for that. This particular proof is going to be quite math heavy. It's going to involve a lot of calculus, so bear with me. It's going to be quite challenging, but I hope that by the end you'll understand it. Now, in order to calculate the velocity of our footballer at any particular point in time, we need to differentiate its position vector. So we know that our velocity vector, which is our velocity at any point in time, let's say right here, is just going to be equal to the derivative with respect to time of our position vector, right? And we know that from our math class that if we were to differentiate our position vector, that's the same as differentiating both elements within our vector. So that's the same as saying, in other words, d dt of r cosine theta and d dt of r sine theta. So that's essentially what that means. So how do we solve that? Well, first things first, we've got to note that r is actually a function of time. It's unlike circular motion. We can't assume r is constant, right? R is a function of time. So we'll have to use two really interesting mathematical rules here in order to do this. One is the product rule. I'll remind you what that is. The product rule is d dt of u and v, where u and v are functions of time, is going to be u dot v plus v dot u. Right? That's the product rule. I won't go into a proof of that, but that's from your math class. Another thing which we're going to be using in this particular video, in fact, let me zoom out. Another thing we're going to be using in this video is d dt of some function of theta, which is a function of time, is going to be equal to df dt times, it's just df dt, and that's going to be equal to, using the chain rule, df d theta times by d theta dt. Right? So in other words, we can write that that's equal to the differential of f times by theta dot. Right? Both of these formulas will play a huge part in this video in determining our equations of motion. So I definitely recommend you familiarize yourself with these formulas before you join me in trying to uncover what the equations of motion are. Okay, so let's get started. This is v. Let's see, in order to calculate the derivative of this, we need to use the product rule right here. So that's just going to be equal to r dot, that's actually, that's going to be equal to r dot. That's I'm differentiating this one right now. That's r dot times cosine theta, and now it's time for r to remain the same, and then we derive cosine theta, and that's going to be equal to, what's the derivative of cosine theta? Well, we're going to use this formula right here. That's going to be equal to minus sine theta times by theta dot, right? And what about this one? What about this bottom element? That's going to be r dot times by sine theta plus r times by the derivative of sine theta is cosine theta times by theta dot. Okay, I hope that makes sense. This is just a small part. Now the hard part comes, and that's calculating the acceleration. This is a much more challenging thing because we actually have to use this rule many times in order to solve it. But that's our velocity vector. We know that our acceleration is just d dt of our velocity vector, right? In fact, let me zoom out a little bit more so you can see all this. Yep, our acceleration is equal to our dv dt. So we're going to try and solve that, and remember, I'll write it out for you again. This will be equal to d dt of your top element, r dot cosine theta, plus r times by minus sine theta, theta dot, right? And this is going to be d dt of sine theta, sorry, r dot sine theta, plus r times cosine theta, theta dot. I've just rewritten this and differentiated. So this becomes a matter of really, really heavy, involved calculus. So bear with me, it's going to be quite challenging, but I think we can do it. First of all, we need to differentiate this term right here because we know the differential sign is distributive, so we can write that as r double dot times cosine theta, plus r dot times whatever the derivative of cosine theta is, which is minus sine theta, theta dot, because remember we're differentiating with respect to time, not theta, right? And now we're going to add that to whatever the derivative of this is. I'm going to call this u, and I'm going to call this entire term here v, right? That's how I'm going to differentiate this. So that's going to be r dot times by minus sine theta, theta dot, plus r times by the derivative of whatever this beast is. I don't know what it is, so I'll just leave it as the derivative of minus sine theta, theta dot. I don't know what that is just yet, so I'm just going to leave the derivative sign in there. Alright, now it's time to evaluate this bottom element. First of all, let's do this one. That's going to be r double dot times sine theta, right? And now we're just adding that to r dot times by the derivative of sine theta, which is just going to be equal to cosine theta, theta dot. And that's going to be added to, now that we've sorted out this term, now let's do this term. That's going to be equal to r dot times by, what's the derivative of, well, actually no, it's just going to be cosine theta, theta dot. And then we're going to add that to r times, well, we don't know what it is yet, but it's going to be equal to the derivative of cosine theta, theta dot. Okay, we're getting there. We've done the hardest part. Now it's just more a matter of simplifying, if anything. So let's do that. Let me just scroll around to give myself more room. That's going to be equal to, let's see, it'll be r double dot cosine theta. Notice these two are the same, so I can add them. That's going to be minus 2r dot sine theta, theta dot. That's a good start. We're already starting to simplify things. And now I'm going to add that to r times by whatever the derivative of this is. So let's get on that. That's going to be equal to, what's the derivative of minus sine? That's going to be negative cosine times theta dot. And that's going to be times by theta dot again. And that's going to be added to minus sine theta times by theta double dot. All right. I know I'm kind of rushing through this, but I don't want to be here forever, and I don't want to be going so slow on each part that it'll take too long. But I hope I'm not losing you regardless. So that's that. That's this term simplified. Let's see if I can do the bottom element now. That's just going to be r double dot sine theta plus, well, let's see, these terms are the same, so I can add them as well. So let me do that. That's going to be plus 2r dot cosine theta, theta dot, right? And we're going to be adding that to r plus the derivative of this term, so we're going to do the same thing we did before. We're going to treat this as u, we're going to treat this as v. So that's going to be equal to, let's see, what's the derivative of cosine theta? It's going to be minus sine theta, theta dot, and that's times it by theta dot, because that's v. And we're going to be adding that to cosine theta. Now it's this term to get differentiated, and that's going to be theta double dot. Whew, okay, we're getting there. Let's see if we can simplify that a little bit more now. We sure can. I'm going to use the notation of theta. Actually, let me write this down. I'm going to use the notation theta equals theta. Theta dot is equal to omega, and theta double dot is equal to alpha, because I know if I don't do that, I'm going to make a mistake somewhere along the line. Okay, I'm going to use this notation. So that's the same thing as r double dot cosine theta minus 2r dot sine theta omega. Now we're going to distribute the r around here, so that's going to be minus r cosine theta omega squared, right? Theta dot times theta dot is omega squared, minus r sine theta alpha. Okay, that's this top element done. Let's see if I can simplify the bottom element. That's going to be r double dot sine theta plus 2r dot cosine theta omega minus, and now I'm distributing the r around this bracket just here. That's going to be minus r sine theta omega squared again, and that's going to be plus by r cosine theta alpha. Okay, so we're getting there. We're almost done. Now I'm just going to, we know that because this is just one massive 2D vector, what I'm going to do is I'm going to split this into a whole bunch of smaller vectors under addition, and we know we can do that from math class. So I'm just going to simplify that by writing that's the same thing as r double dot times by cosine theta sine theta, and then I'm going to factor out here a positive 2. So I'm actually going to factor out these terms and these terms. So that's just going to be positive 2 r dot omega times by minus sine theta cosine theta. If you haven't noticed, I'm just gripping these terms right here and these terms right here. I hope I'm not losing you. So I'm just grouping them into different terms and adding them together, because we know we can do that. So that's that one sorted. Now let's get on these two terms. We can add them together. That's going to be equal to, well, what will it be? Let's factor out an r and an omega squared. That's going to be r omega squared times by minus cosine theta minus sine theta. And then let's now group these two terms. That's going to be equal to, let's factor out an r and an alpha. R and an alpha, that's going to be minus sine theta cosine theta. Alright, so we're getting there. Let me zoom out just a little bit more so we can see most of this. Alright, so this is our acceleration vector. Whew, I told you it would be quite involved in calculus, didn't I? And indeed it is. But notice we're not completely done here. I've got a sneaking suspicion that we can simplify these terms right here. Notice they're still vectors involving sine thetas and cosine thetas, right? We can actually simplify these quite a bit in order to get a much more familiar expression. So let's do that real quick. Well, we know that this is our generic equation of motion. This is what it looks like, right? And this is our position vector here, right? But let's create a new axis. Before we had our j unit vector here of magnitude 1, and we had our I unit vector here of magnitude 1, right? Let's, for the sake of simplicity, create a new axis. So let's call this our tangential unit vector, ET, and let's call this unit vector heading towards the inside of our path, EN. Right? And because they're unit vectors, they all have a magnitude of 1, right? And I'm going to try and describe these new unit vectors I've created in terms of the I and j unit vectors that have already existed. So bear with me. Let's see if we can simplify our unit vector heading towards the inside of the circle. Well, this is En, and it's going to have a magnitude of 1. But we know we can draw two triangles. We can draw a triangle out of this. We know that this is theta, right? Because this is theta, right? So that means this is going to be 1 sine theta, and this is going to be 1 cosine theta, right? But notice that this is heading down, and this is heading to the left, right? Meaning that it will be negative cosine theta times the I unit vector plus negative sine theta times the j unit vector. So let me write that down. That will be En is going to be equal to, what will it be? It will be negative cosine theta and negative sine theta, right? Okay, I hope that makes sense. So that's going to be a big part to play, right? And you might be starting to connect the dots here that this might be able to be substituted into this equation. But bear with me. I'm going to do one step at a time. So let's also get the tangential unit vector I just created in this picture. This is going to be our tangential unit vector, right? We can also create a triangle out of this in I and j unit vectors. This is going to have a magnitude of 1, right? This right here, if we create an imaginary line just here perpendicular to that and continue this line over, we know this angle is going to be equal to theta, right? Just imagine it. It's kind of like saying dot 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 right here. This right here is theta, and imagine creating a dotted line just over here. That means here that this is 90 minus theta, which means that this is theta. Okay, I hope that makes sense. I'm kind of rushing through this, but I'm assuming our geometry skills are okay. Meaning that this is going to be 1 sine theta, and this is going to be 1 cosine theta. These are the magnitudes of these position vectors. So let's get started. This means that ET now, remember this is our ET, this is our unit vector just here, can be written as, what's it going to be in our x direction? Well, it's going to be facing to the left, right? So that means it'll be left, right. It'll be facing to the left, okay? So that'll be minus sine theta here. And this is going to be facing positively upwards. So that's going to be plus cosine theta right there. Okay, I hope that makes sense. These two formulas will play a huge part, right? Because we can substitute them now directly into here. Let me zoom out just a little bit more. I wonder how much I can zoom out before you stop being able to not being able to read this. But let's see if I can use that over here. That's going to be equal to our acceleration vector. In fact, let me zoom in a little bit. I'm afraid you can't see that. There we go. I hope you can see that now. Our acceleration vector is equal to r double dot times by, well, what's cosine theta sine theta? What's this right here? Well, that's the same thing as negative En, right? That's the same as negative En if you just distribute the negative sign, right? So that's going to be negative En, right? What about this term? Plus 2r dot omega. What about this term right here? That's going to be equal to, well, what's that? Minus sine theta cosine theta? That's this one. That's ET right there. That's ET. So that's going to be times by ET, our unit tangential vector, right? And we're going to be adding that to this term, which is going to be r omega squared times by, well, what's this? That's going to be En, right? So that's going to be En just there. And we're going to be adding that to r alpha times by, what's this? Well, that's going to be minus sine theta cosine theta, which is ET. So let's do that. That's ET. Okay, I hope that makes sense. So let's go into simplifying that now. We can group the ENs and we can group the ETs. So let's do that. First, I'll group the ETs. That'll be equal to 2r dot omega, that's this one taken care of, plus r alpha, and that's going to be all times by our tangential unit vector. And that's going to be added to, now let's group our ENs. So that's going to be minus r double dot, that's this one sorted, right? So we've sorted out this one, and now the last one left is plus r omega squared. All right, and that's going to be times by En. Okay, that's a lot to swallow at this point, but this is our answer. if you think about it, this is actually a really beautiful equation because it's so generic. It can describe any continuous path, not just a circular path. This is one step above that, if you like. In fact, you can imagine if you consider if r is equal to a constant, right? Just like with the case of circular motion, then what do we get? Then we get our acceleration vector is equal to, well, that's going to be 0 because here we've got r dot and the derivative of a constant is 0. In fact, let me make these dots a little bit clearer. Here we've got r dot, so that's going to be 0. We're going to be adding that to r alpha times et. And we're going to be adding that to, well, what's r double dot? Well, it's going to be 0 because r is a constant plus r theta dot. R omega squared. So times by En, right? And if you simplify that down, remember this is only for r is equal to a constant, right? So if you simplify that, you're left with our acceleration is equal to r alpha et plus r omega squared En, right? What does this remind you of? This is our circular motion formula we derived in our previous video. It's the same thing as this more generalized equation, but for the case where r is equal to a constant. Okay, I hope that makes sense. So this is for circular motion. And this is a much more generalized case, which is going to be used for a whole bunch of different practical examples, right? I should also mention, and I'm running out of time here, so I won't actually go into the laborious proof of it, but you could have also simplified your velocity vector as well by writing out our velocity vector is minus r dot En plus r, let me just scroll over, plus r omega et, right? That's going to be another formula to play. And we could easily done that the exact same way we did our acceleration vector, just by substituting in our new coordinate system. But these two formulas, I really cannot overemphasize their importance. They are going to be huge to play in the future when we calculate problems which involve arbitrary continuous paths.